Hello, welcome to this video. Today we're going to show that for all A, B, and C that are positive numbers, the inequality a squared plus b, a squared over b plus c, plus b squared over c plus a, plus c squared over a plus b is bigger than or equal to a plus b plus c over 2. So, let's begin. And I'm going to show two ways to do this. First of all, I'm going to show the way which is one line. Then I'm going to show the way that is a couple more. So for the first short solution, we're going to use Holder's inequality. And Holder's inequality, if you don't know, states that for all AI and bi and alpha and beta that are bigger than or equal to 0, we have a1 plus a2 all the way on to plus an to the alpha times b1 plus b2 all the way on to plus bn to the beta is bigger than or equal to a1 to the alpha, b1 to the beta, all this to the power of 1 over alpha plus beta, and then the same thing for a2 and b2 up until an to the alpha, bn to the beta of the power of 1 over alpha plus beta, and then this entire thing to the power of alpha plus beta. This is Holder's inequality, and we're going to use it to get rid of these denominators. So what we're going to do is say this is the cyclic sum of a squared over b plus c, and if I multiply this by the cyclic sum of b plus c, you can see how when we use Holder's inequality, the denominator will disappear, and in our case we have this alpha is 1, this beta is also 1, and so this is bigger than or equal to, if we just, this is a1 to the alpha, in our case it's a1, b1 to the beta, in our case it's just b1, so it's just multiplying these together, and so it's going to be the cyclic sum of the product of these, which is a squared, but then we have to take this to the power of 1 over alpha plus beta, which in our case is just 1 over 2, which is just the square root, and then we also need to square this entire thing, because this entire thing is also to the power of alpha plus beta. But now we can see the square root and the square cancel out, and we get the cyclic sum of a squared. Now notice, what is the cyclic sum of b plus c? This is, what we can do is shift it along cyclically, so b gets shifted to a, we can shift b backwards to a, and c we can shift forwards to a, to get this is the cyclic sum of 2a, or 2 times the cyclic sum of a. And now, we know that this is equal to this, so we can just divide by this number to get that, the cyclic sum of a squared over b plus c, which is this, is bigger than or equal to this divided by this, but the cyclic sum of A cancels out, and we just get the 1 left at the numerator divided by the 2, which is this 2 right here. And this is precisely A plus B plus C. So we've proven the inequality. Now, let's go on to the second solution. Alright, our second solution is going to use what's a technique which is called SOS, which stands for two things: save our souls, and the more normal one in this case, sum of squares. We're going to show that if we move A plus B plus C over 2 to the other side, we can rearrange things and combine numerators and denominators in such a way that we get a sum of squares which will be bigger than or equal to 0, which will prove our inequality. So we have the cyclic sum of A squared over B plus C, and then we want minus this, and so this is just the cyclic sum of A over 2, so I can just bring A over 2 into this cyclic sum. And now I'm going to take this 1/2 out and add these fractions, and so I get A times 2A minus B minus C over B plus C. If you don't trust me, you can check it for yourself. That is what we get. And now, this is the cyclic sum of A times A minus B over B plus C. And this is minus A times C minus A over B plus C. And now we can shift this cyclically forward. So A is replaced with B, C is replaced with A, and B is replaced with C. And so we get 1/2 the cyclic sum of A times A minus B over B plus C minus B times A minus B divided by C plus A. And now we will combine these numerators, and notice A minus B is a common factor, so we'll be able to take it out quickly. So this is A minus B times the fraction A times C minus A, which is A squared plus AC, minus B times B plus C, which is minus B squared minus BC. And so, and in the denominator we have B plus C times C plus A. And now, notice that we're able to, we can combine this. So A squared minus B squared is A minus B times A plus B, and AC minus BC is A minus B times C. And then if we combine those together, we get A minus B times A plus B plus C. So this is half the cyclic sum of A minus B, which is this, times another A minus B, so this gets squared, times A plus B plus C, divided by B plus C times C plus A. And now, notice what we have here is a sum of squares, as because A, B, and C are positive, A plus B plus C and B plus C and C plus A are positive, and A minus B, which before or earlier we weren't really sure if it's positive or negative, we actually have it squared, so this is definitely positive, or at least bigger than or equal to 0, and a half is of course bigger than 0, and so all in all, this is bigger than or equal to 0, and then if we just move the cyclic sum of a over 2 to the other side, we proved our inequality once again. And I also remember there is a proof with AMGN, which is that the algebraic mean is bigger than or equal to the geometric mean. I remember there was a proof of this using it. I don't remember how to prove it. I don't remember the proof. So if you do find it, maybe put it in the comments, and I'll have a nice aha moment. So finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting content like things like this in the future. And finally, that's it.